In this paper, we extend the explicit forward approximation to the implicit backward counterpart, which can be realized via a recursive neural network named IM-block. Moreover, multi-level fusing mechanism and residual channel attention block are adopted to boost performance of our network. Our goal is to establish a single but efficient network to reconstruct a clean image from the natural hazy image. Here is an example. Our key motivation is modifying the architecture of residual block in order to achieve the better performance. Considering the original objective of ResNet is to tackle the problem of vanishing gradient and the fact that low-level CNN networks are usually shallow networks with limited layers. Since the vanishing gradient problem hardly appeared in shallow network, the residual structure is suboptimal in low-level tasks. Based on this observation, we attempt to determine an optimized structure in low-level tasks. Noticing that many recent work have applied ordinary differential equation (ODE) to explain the architecture of CNN, we introduced the Euler method in ODE to modify the ResBLOCK. In Euler scheming, ResBLOCK can be viewed as explicit Euler scheming. So what about implicit Euler scheming? To verify our conception, we set a simple instance to compare the stability between explicit scheming and implicit scheming. Firstly, we set formula 1 as the derivative of y with the perspective of t equals minus ay. Is the intuition to determine the analytical solution. But using the explicit scheming and the implicit scheming to approximate the analytical solution, the solution can be expressed as formula 2 and formula 3. It can be found that implicit Euler scheming is unconditionally stable, but explicit Euler scheming is conditionally stable, given that the IM block will have better generality and stability. Sure, the CNN structure of ResBLOCK and IM block are expressed respectively. Since the implicit algebraic equation cannot be solved analytically in general, an iteration method is generally used to determine xk plus 1. The processing progress between xi and xi plus 1 can be replaced by an iteration approaching progress. In order to get the feature in different levels from shallow to deep, we cascade 3 IM blocks with different function f, and the different level features x1, x2, and x3 will be shuffled and combined in the merits of each feature. These 3 images are decoded from the features from 3 different level features, x1, x2, and x3. It can be seen that shallow features x1 still keeps dense haze. The deep features have slight haze, but deep features have color distortion and serious artifacts. To overcome the drawbacks of different level features and combine the merits, we adopt multi-level fusion frame. It's easily understand that the features x1, x2, and x3 as parameters distributed in different channel, different pixel location. Since the artifact, haze, and color distortion distribute in different channel and different pixel location, after the concatenate feature processed by the convolution layer, the convolution layer will be output weight matrix W1, W2, and W3, including channel and pixel location information. The final result is the combination between feature X and weight matrix W. The residual channel attention block contains a convolution layer and global average pooling layer, multi-layer perceptron, and sigmoid layer. The convolution layer transforms from the 64 channels feature to 3 channels features. The average pooling layer outputs a parameters average in each channel. The multi-layer perceptron gives each average a weight parameter as its weight. The factors determining the weight depends on hazy level, artifact level, etc. It can be seen that comparison between the network with RCA-block and without RCA-block. The network with RCA-block has better performance with the aspect of optic condition and color distortion. The architecture of multi-level implicit network is as shown in the image. IM-block is illustrated in dashed box. IN and DCON in MLE denotes instance normalization and dilated convolution respectively. Times N in MLE represent the dilated rate, and the dilated rates are different from each IM block. DCON in decoder represent fractionally strided convolution. MLF and RCA block has introduced before. The encoder will transform the image from RGB space into feature space, and for the decoder, vice versa. To demonstrate our performance, we present several results on different datasets and also real images. For the SOTS synthesis dataset as the benchmark dataset, the result is nearly the same as the ground truth. On the extra synthesis dehazing dataset test A, our result also do a very good job and recall the shampoo on the bottom right corner. Moreover, on the MiddleBury synthesis dataset, a high-resolution stereo dataset with sub-pixel accurate ground truth, the result outmaneuver most of the state-of-the-arts. For the real image, our network also get a very well result. Thanks for listening.